The most distant human-made object in existence is NASA's Voyager 1 spacecraft, a tiny robotic traveler that has achieved something once thought impossible. It has reached interstellar space, venturing far beyond the planets and borders of our solar system. Launched over 45 years ago, it still sends data back to Earth from the uncharted darkness, continuing to explore areas it was never expected to reach. Originally designed for a brief mission to study the outer planets, this aged spacecraft powered by technology older than cassette players has outlived its projected lifespan by decades and continues to redefine the boundaries of space exploration. Even more remarkable is the fact that Voyager 1 and its twin, Voyager 2, operate on less computing power than a digital wristwatch. And yet, these resilient probes continue to function in a realm of space so distant that light from the sun takes over 20 hours to reach them. Recently, a new discovery from Voyager 1 has once again ignited curiosity across the globe and left the scientific community astounded. Although the spacecraft is billions of kilometers away, it has detected something unusual, something that might reshape our understanding of the universe. But to truly appreciate what makes this find so fascinating, we must look back at how this extraordinary mission began. It all started with a key moment in space history, a moment born from the insight of Gary Flandreau of NASA's Jet Propulsion Laboratory. With nothing more than a pencil and paper in the early 1960s, Flandreau mapped out a revolutionary route that would allow spacecraft to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, by harnessing the gravitational power of each world. In the late 1970s and early 1980s, these four gas giants aligned in a rare cosmic configuration, forming a kind of celestial highway that occurs only once every 176 years. With this alignment, a spacecraft could be slingshot from one planet to the next, each gravitational encounter giving it a boost in speed and trajectory, reducing a journey that would typically take 30 years down to just 12. Recognizing this once-in-a-lifetime opportunity, NASA moved quickly. In the summer of 1977, just 15 days apart, they launched two identical spacecraft, Voyager 1 and Voyager 2. Their original mission was modest in comparison to what they would eventually accomplish, simply to capture detailed images and data from Jupiter and Saturn. No one could have imagined at the time that these twin spacecraft would become the most successful and long-lived space explorers in history. In the first stages of their journey, Voyager 1 and 2 returned the most detailed and breathtaking images ever taken of the outer planets and their moons. They gave us our first close-up look at Jupiter's violent storms and Saturn's majestic rings. They revealed dynamic and unexpected phenomena like erupting volcanoes on Jupiter's moon Io and the icy, fractured surfaces of Saturn's moons, suggesting active geology and potential subsurface oceans. Voyager 2 alone achieved the unprecedented feat of flying by Uranus in 1986 and Neptune in 1989, becoming the only spacecraft to study these distant ice giants up close. These encounters transformed our understanding of the solar system, showing us that these remote worlds were not dead, static places, but dynamic and varied, full of surprises and mysteries. The spacecraft themselves, roughly the size of a Volkswagen Beetle, were launched using the most advanced technology available at the time. But by today's standards, they seem almost quaint. Each spacecraft contains about 69 kilobytes of memory, a laughably small amount compared to even the most basic modern smartphone. Data collected by the onboard scientific instruments was stored on track tape recorders and transmitted back to Earth using a radio transmitter powered by a mere 23 watts, less than the energy required by a light bulb. Communication relied on a 12-foot wide satellite dish and carefully timed transmissions that traveled at the speed of light, taking more than 18 hours to reach Earth from the edge of the solar system. As the probes moved farther and farther away, radio interference from Earth-based technologies like cell phones, Wi-Fi, and satellites made communication increasingly difficult. Still, the Voyager spacecraft pushed on, delivering science from the edge of the known universe. The Voyager missions did more than just photograph the outer planets. They ventured into the unknown, paving the way for our understanding of interstellar space. After more than 3 decades of travel, both spacecraft reached the outermost layers of the heliosphere, the giant bubble created by the solar wind that encases our entire solar system. Outside of this bubble lies interstellar space, a realm filled not with emptiness but with mysterious plasma, energetic particles, and magnetic fields shaped by distant stars and galactic events. The transition from the heliosphere to the interstellar medium occurs at a boundary known as the heliopause, originally estimated to be about 50 astronomical units from Earth. When Voyager 1 crossed this boundary on August 25, 2012, it provided definitive data for the first time in human history from the space between the stars. Contrary to expectations, the crossing was not marked by an immediate or dramatic change. Scientists had anticipated a sudden increase in the number of cosmic rays and a distinct change in the orientation of the magnetic field, assuming the probe would enter a region influenced by the magnetic environment of nearby stars rather than the Sun. Surprisingly, while Voyager 1 did record a significant spike in plasma density consistent with interstellar space, it did not detect any noticeable change in the magnetic field's direction. This contradiction puzzled astronomers and raised new questions about how the Sun's magnetic influence extends into space and whether the boundary of the heliopause is more complex or porous than previously thought. Voyager 2, following a slightly different trajectory, crossed the heliopause in November 2018 and confirmed many of the strange findings first observed by Voyager 1. Both probes are now in the interstellar medium, slowly making their way toward the theoretical edge of the Oort cloud, a vast distant shell of icy objects that marks the furthest reaches of the Sun's gravitational influence. Although the Oort cloud has never been directly observed, scientists believe it could stretch nearly halfway to the next star system. The journey toward this distant region will take tens of thousands of years. But even if the probes cease to function long before they get there, they will continue to drift silently through space. Each spacecraft carries a copy of the Golden Record, a metal disc containing music, images, and sounds of Earth intended for any intelligent life that might one day find them. The Golden Record, curated by a team led by Carl Sagan, remains one of humanity's most poetic gestures, a cosmic message in a bottle cast into the ocean of stars. As we look back on more than 4 decades of Voyager discoveries, it's clear that the mission has forever changed our view of space and our place in it. What began as a modest planetary exploration has turned into an enduring testament to human curiosity and engineering. The spacecraft may be aging and their power sources slowly diminishing, but their legacy grows with each transmission, each strange particle, each whisper from the dark. Whether they discover new cosmic phenomena, chart unknown regions of space, or simply continue to move silently through the void, Voyager 1 and 2 are symbols of what humanity can achieve when it dares to dream beyond its own world. Their story isn't just one of scientific achievement. It's a story of perseverance, wonder, and our unyielding desire to reach for the stars. The fact that the Voyager spacecraft are still operating more than 45 years after launch is nothing short of a technological miracle. Engineers designed them to last just 4 years, long enough to reach and study Jupiter and Saturn. Yet, both spacecraft have endured the harsh radiation belts of gas giants, the freezing cold of deep space, and the increasing challenges of communication over such vast distances. Every year that passes brings new engineering hurdles. The spacecraft's power source, plutonium-238 in radioisotope thermoelectric generators, or RTGs, is steadily weakening. These RTGs convert heat from radioactive decay into electricity, but they lose about 4 watts of power every year. This means mission engineers must periodically make difficult decisions about which instruments to shut down in order to conserve power for the most critical systems. Each shutdown feels like saying goodbye to a part of the spacecraft's sensory perception. And yet, even operating with only a fraction of its original instruments, Voyager continues to deliver valuable data. In recent years, Voyager 1 began transmitting information that puzzled NASA scientists. Its data showed that even in the vast emptiness of interstellar space, there are still ripples, variations in plasma density that indicate waves of energy moving through the medium. One such detection, nicknamed the plasma hum, was a faint but persistent vibration in the interstellar medium. Unlike the sharp changes caused by solar outbursts or cosmic events, this hum was constant and suggested that space between the stars is far from silent. This detection, first made in 2017 and later confirmed through analysis of long-term data, provided new insight into the nature of interstellar space, a realm once thought of as completely quiet and inert. The fact that Voyager 1 could detect such subtle changes with decades-old instruments is a testament to the precision and resilience of its design. Meanwhile, Voyager 2, traveling on a slightly different path through the southern hemisphere of the heliosphere, offered a rare opportunity for comparison. Its 2018 crossing of the heliopause was better observed and more clearly marked than Voyager 1's, confirming that the solar wind's influence ends in a more defined region than previously thought. This dual perspective helped scientists build the first three-dimensional model of the boundary between our solar system and interstellar space. The heliosphere, once thought to be a uniform bubble, was revealed to be more like a comet, elongated and uneven with variations in shape and density. This realization forced scientists to rethink how our solar system interacts with the galaxy around it. It also introduced new questions. What lies beyond the heliosphere? How does the galactic environment influence the formation and evolution of solar systems like our own? Though the scientific instruments on board the Voyager spacecraft are now limited, the probes remain invaluable for space weather monitoring. They continue to measure cosmic rays, high-energy particles that originate from supernova explosions and other violent galactic events. Within the heliosphere, the Sun's magnetic field and solar wind deflect most of these particles, protecting Earth and the other planets. But beyond the heliopause, this protective bubble vanishes. The rise in cosmic ray density detected by both Voyager 1 and Voyager 2 confirmed their entry into interstellar space and provided direct data on the kind of radiation environment a spacecraft or even a future interstellar traveler would face outside the solar system. Such measurements are vital for the planning of future missions, particularly those involving human exploration beyond Mars. Understanding this radiation environment can help scientists develop better shielding technologies and anticipate the health risks posed to astronauts by prolonged exposure to deep space. Beyond the science, the Voyager missions have also had a profound cultural impact. They have inspired generations of scientists, writers, and dreamers. The golden records attached to both spacecraft serve as a poignant reminder that while these probes were designed as scientific instruments, they also carry with them the hopes and identity of humankind. Each record contains greetings in 55 languages, sounds of nature such as thunder, birdsong, and the roar of the ocean, as well as 90 minutes of music ranging from Bach and Beethoven to Chuck Berry's Johnny B. Good. There are also 116 images encoded on the disc showing scenes of life on Earth: children eating, people laughing, athletes in motion, and even a diagram of human anatomy. Curated by Carl Sagan and his team, these records are a time capsule for alien civilizations or perhaps for future humans to one day discover. They offer a snapshot of who we were at a specific point in time, broadcast into the galaxy with no certainty that anyone will ever hear them. And yet, they symbolize something deeply human, a longing to connect, to be known even across the vastness of space and time. Despite their age and limited capabilities, the Voyager probes continue to make headlines. In 2020, Voyager 2 transmitted data from more than 18.8 billion kilometers away, prompting scientists to reflect on the sheer scale of its journey. That same year, the probe briefly went silent due to an issue with its onboard computer. NASA engineers, using the same Deep Space Network antenna that had tracked the mission since launch, managed to re-establish contact after several months of painstaking work. The moment communication was restored, cheers erupted from the mission control team, a testament to the emotional and intellectual investment these machines have inspired over decades. Each time one of the Voyagers sends a signal home, it reaffirms our commitment to exploration, curiosity, and the pursuit of knowledge, even when it pushes the limits of what seems possible. As Voyager 1 and Voyager 2 continue their lonely paths into the cosmos, their eventual fate is one of eternal wandering. Long after their power sources deplete and their transmitters fall silent, they will continue to drift through the galaxy as silent ambassadors of Earth. They may one day pass near another star, perhaps billions of years from now, carrying their golden discs like cosmic business cards. If some distant intelligence encounters them, It may wonder at the civilization that built such relics, powered them with radioactive decay, and filled them with music, laughter, and science. More likely, they will remain undisturbed, silent witnesses to the passage of time, orbiting the Milky Way's center once every 225 million years. But while their physical journey continues, the symbolic journey of the Voyager spacecraft has already reached far beyond our expectations. They've shown us that even the most ambitious goals, like touching the stars, can begin with a single launch and a belief in what lies beyond. They've demonstrated that technology, no matter how simple by today's standards, can be resilient and effective when guided by thoughtful design and purpose. And they've reminded us that space is not just a cold void, but a realm filled with patterns, pulses, plasma, and promise. With each pulse of data they send back, these robotic explorers whisper stories from the dark frontier, stories that continue to teach, to provoke wonder, and to inspire. As NASA plans new missions to the outer planets and even interstellar space, the legacy of Voyager endures. Concepts like the Interstellar Probe, a next-generation mission that would aim to travel far beyond the heliopause within a human lifetime, are being actively discussed. These future spacecraft would build on the path forged by the Voyagers, carrying more advanced instruments, traveling faster, and communicating with greater clarity. But even as new technology replaces old, the spirit of Voyager remains unmatched. It was a product of its time, but its impact spans all times. Its success teaches us not only about the nature of the universe, but also about the power of long-term vision and the beauty of open-ended discovery. In the end, the Voyagers are not just space probes. They are storytellers, historians, emissaries, and explorers. They are proof that humanity can build machines capable of traveling into the infinite, capturing echoes of the birth of stars and the faint hum of the universe itself. They represent the best of what we are and the greatest of what we can become. As long as they travel, and even after their voices fade, their story will remain one of the most enduring sagas of our time. A tale of wonder, of resilience, and of reaching for the stars with outstretched hands and open hearts.